Hello, hello, and welcome to Learn Extra. My name is Abram. It's a lovely Tuesday. You know, it's time for us to learn more and learn extra together. I hope you enjoyed your day at school, and we're going to be together, but I'm not alone. I'm with Tracy. Look who's back. Tracy,
Hey,
how are
back.
you, Tracy?
Very well, thanks,
Okay,
Abram.
welcome back officially
Thank
from
you.
me.
Thank you.
And I see you're not alone. Congratulations.
Thank you.
I hope
I've
she grows.
had my little baby girl, and she is doing beautifully. Thank you.
She's growing so fast. I saw the pictures. Congratulations.
Thank you so
She's so
much.
adorable.
She is really.
Right. Talking about what we're doing today. What are we doing?
Mindset is we are tackling emotion, and this is we're going to introduce motion, speed, velocity, acceleration. So it's going to be a kicking show. Brilliant.
Awesome. It's going to be a kicking show. Well, I can't wait for that. Join us on our social networks. Facebook, it's at facebook.com/LearnExtra. And on Twitter, follow us at LearnExtra. On on our Facebook page, already there are notes posted for you, the download, the view, and the test yourself links. On the test yourself links, if you answer them correctly, you stand a chance of winning this awesome Casio calculator. But even if you don't get them correctly, if you've tried, you're also being entered to a draw. So enter not just to win, but to test yourself and to challenge yourself. There are so many other giveaways that we're having, but for now, let's keep it on our Facebook page. Chat with us if you're struggling, if you need some help. We're here for you. Back to you, Tracy.
Thanks, Abram. So mindset is we said, what is motion? And if you think about it, all the various different things that move. We'll talk about bicycles going. We'll talk about cars and buses and trains. There's so much in our physics section that is based on motion. And next year you're going to go into forces, and that links with motion as well. So incredibly, incredibly important section. And we're going to start with motion in one direction now in grade 10. So we've got some definitions to define. We want to know, what do we mean by distance and displacement? Now, those are two very similar but also very different concepts. And we started by talking about them last week. So we'll recap distance and displacement. We want to define speed and velocity, as well as acceleration. So lots of new concepts, but a lot of them are intuitive. You have driven in a car or in a taxi or ridden on a bicycle, or as you walk along the road, you're going to be moving, and so that motion is what we're going to be talking about. We will also consider the vector nature of things like displacement, velocity, and acceleration. And you know, we love to solve problems, because mindset is, this is an amazing section of work. There's a lot of maths, so that calculator would be very, very handy. And so make sure you've got a calculator with you, or if you haven't got a calculator, please go and try those test yourself questions and enter the competition. It's an amazing opportunity to get a great calculator. So, lesson description, we've gone through. Let's talk through our challenge question. Now, for the challenge question today, I need you to go and find a friend. Brother, sister, friend, someone who's going to be with you, because Abram and I are going to do this together later, but I want you to go and challenge yourself on this. We're doing a little informal experiment, and that experiment needs you with a friend and a cell phone and a way of timing. So, join up with a friend and time how long it takes to type LOL single-handedly on a cell phone. The context of this is, imagine a person driving a car, because I know you would never do this, but one day person's got their license and they're driving their car and their cell phone buzzes. And so they pick up their phone and they want to reply to the other person. And they start typing on their phone. And you know how many car accidents occur because of people typing on their cell phone? Have you heard of that, Abram? So absolutely, lots of car accidents happen because of people being distracted by their cell phones. So I want you to go and time how long it actually takes you to type LOL. Just LOL. Most messages are longer, but just LOL. Then we're going to record each time in a table, and those will be our data points. We will complete the table with headings and calculate an average time. So I've given an example of a table. You can fill that in. And then we would need to take that average time and calculate how far a car traveling at the different speeds would travel in the time it takes. using your average time. And so we've got a car. What happens if the car was going at 60 kilometers an hour, or 100 kilometers an hour, or 120 kilometers an hour? So you need to think through that. And then give a discussion. In light of your research, what would you say to advise people about texting while driving? Provide some reasoned arguments. So you've got to really think through, how safe is it? What could happen during that time? But you've got to be able to go back to your data and argue your point. So very important that you think through these types of questions. Now, we want to go into the summary because, as I said to you at the start of this section, there's lots and lots of definitions that we need to make sure we've got clear in our mind. When we speak about motion, we are speaking about things moving. And always when we talk about things moving, we need to have a frame of reference which gives context to the positioning or the movement of various objects. So I could say my frame of reference is a reference point with a set of directions. So an object is 2 meters away from the flagpole and is moving east. The motor car is driving north at a speed of, okay, all those types of things. We need to have a frame of reference which, with a set of directions that will give us some understanding or some context to that motion. Then we need to speak about position. Now, position is where something is. It is located at a specific point with respect to a frame of reference. So it's where the object is located with respect to a chosen reference point. Then we go into displacement. Now, the displacement of an object, keyword, is how far it is from the chosen reference point. But it is the shortest distance from that chosen reference point to now the position that it has been positioned in. It is the shortest distance between the object and the reference point, and that keyword, shortest distance. It has magnitude and direction because it is a vector. Now, I'm going to go down to the bottom of this page and give ourselves a bit more space. And when I say displacement, I'm considering the displacement from point A to some point over here, point B, will be the straight line joining those two, and remember it's a vector, so we would have an arrow. In comparison, distance. Well, for a person going, we've got a dotted line here. Let's just take that away. For a person traveling from point A to point B, they could go on a roundabout route to get there. They could walk around this side and then around the bush down there and across to the shop and eventually get to point B. So when we speak about distance, the distance they could walk could be a far long distance, much longer, but that is the path that they took. And so distance, we often speak about distance as being the path taken. And you notice that the distance and the displacement are very different. The distance incorporates all the path that the person took when they got, but the displacement is the straight line from their starting point to their end point. Very important to get that distinction. So we had displacement, how far it is from a reference point. It is the shortest distance. It is a vector. Whereas the distance is the length of the path traveled from start to the end. It has magnitude only. It is a scalar. Now, speed versus velocity. The speed is the distance covered divided by the time. And we should be quite familiar with that. You've had kilometers per hour. It is a distance value divided by time value. So that would be the speed at which an object is traveling. In comparison, velocity is the displacement divided by the time. So we had speed was distance divided by time, whereas velocity is the displacement divided by time. Now, very often speed and velocity are the same. If this object is moving in a straight line, then and not going on some roundabout way, then the distance and the displacement can be the same. However, sometimes they are not, and you've got to keep your thinking caps on when you consider these, because if an object or a body is going around in a circle and they come back to their starting point, then they have gone a big distance, but have they been displaced anywhere? Do they have a displacement? No, they don't, because they're back at their starting point again. So the displacement would be 0 divided by the time. So sometimes speed and velocity are the same, and sometimes they are not. And you've really got to consider, is the path taken the same as the displacement? And sometimes it is, and sometimes it isn't. So here we've got two equations for the speed. I use the same symbol, v is equal to distance. Sometimes it's given by a capital D, sometimes just delta x as well, if they are the same, divided by delta t. Here, velocity, I'm using the v with an arrow on the top to indicate the vector nature of the velocity, the fact that it has direction, and direction is important. Now, when we write in tests and exams, my understanding is that very often you don't have to put that arrow in, but I've included them in the notes to indicate the vector nature. Delta x is, again, the position. Delta means change in. So if you think about this, if I was drawing a quick graph, a sketch graph, I could have x on the x-axis, and if it moved from a point over there to a point over there, it has changed, and that would be my delta x. It's changed its position. It's moved a certain position across. And so that is why when we speak about horizontal distance, we are considering the change in position going across. In comparison, if I was talking about vertical displacement, then often we would refer to change in y. It's not any different. It's just indicating the vertical. So displacement, delta x, and time, delta t. Velocity is a vector quantity. We've already mentioned that. It would have magnitude. Remember, we said last week magnitude means size, how big something is, and direction. So whenever you're asked to give a velocity, you need to remember in your answer to provide the answer with direction. Then instantaneous speed. Now, if I think of something happening instantaneously, then it's happening in an instant, in a very, very short space of time. So instantaneous speed or velocity is the speed or velocity at a specific instant in time. And so we would speak about an initial velocity or a final velocity. What's happening, what is the velocity or the speed at that exact point in time? Okay? And then lastly, acceleration. Something accelerates, it speeds up, or decelerates, slows down. Acceleration is the change in velocity over a time interval. And so notice this equation is very similar to the one we had previously, except acceleration, again, it's a vector, so it's got that little arrow on the top, is change in velocity divided by change in time. And I said to you there it's a vector, so it's got both magnitude and direction. Now, I would recommend that you get these equations in your mind and make sure that you've got them. Just probably just these last two, because you're going to really, really be able to use them so quickly if you know them and know them well. So we've had the speed or the velocity. Let's talk about velocity. The velocity is the change in the displacement divided by the change in time. And acceleration is the change in velocity over the change in time. Why do I say that about acceleration? Well, if you were to put your foot on the accelerator in a car, you are causing the car to speed up, to change its velocity. And so how quickly it changes its velocity over time would make sense. That's it for the summary. You've got all those equations. Go and make use of them. Go and try that challenge question right now during this ad break. Abram, over to you.
Thank you so much, and welcome, guys. Thank you for joining us. Make sure you get your notes, download or view them. The links are posted on Facebook, so check them out on the wall, or else you can just go to learn.mindset.co.za. Do the challenge question, and we'll see you after the break. Welcome back, Mindsetters. Now, if you just joined us now, you're a bit late, but I'm sure you can still catch up, because we also have got some exciting news for you guys. We have this awesome competition. It is Get Connected with Prizes, proudly sponsored by Vodacom. So this is what happens, Tracy. We've got a set of teachers that the Mindsetters need to vote for.
Brilliant.
I saw your name on the other pictures. So we've got different teachers each for 2 weeks. So what happens, the Mindsetters go and queue, they register using the code, which is LEARN, L-E-A-R-N, and then they choose their teacher, go on Facebook, like the picture of the teacher they voted for.
Cool.
That's your vote, basically. And then if you also share the picture that we have on Facebook that is pinned on top, you get another entry to be put in a draw for airtime now. So we're giving away airtime and 3 Sony Xperia L cell phones. 1 has been won already, so we've got 3. But airtime is galore. So guys, get entering right now. Back to you. And I must say, the Mindsetters should give us their answer for the challenge question.
Absolutely. They need to go and work on those challenge questions, because it's really important that you think about science in everyday life. So really, really important.
Awesome. Let's continue.
Thanks so much. So, Mindsetters, I've got a couple of questions for you. Question 1. Jonty cycles along a straight road at 20 kilometers per hour. So there he is going, pedaling, cycling, focused really, really hard, and he is cycling at 20 kilometers an hour. The questions are asking us to determine his speed in meters per second. So how far is he covering in 1 second? That's what meters per second means. How many meters is he covering in 1 second? Well, how to do that? The question is actually saying to us, can you convert from kilometers per hour to meters per second? Now, I want us to give ourselves a bit more space at the bottom here. And let's write that. Kilometers per hour, we want to change into meters per second. Now, I'm writing this in 2 different ways. I want you to notice I've written kilometers divided by hours is actually also could be written kilometers dot hours to the power of -1. And similarly, meters per second could be written meters per second to the power of meters dot second to the power of -1. The reason for that is because what do we mean by meters per second? We spoke about this last week. It's meters divided by seconds. And I can put that up to the top, but then the exponent must be negative. So don't be afraid of this possibly new form of writing it. The power of -1 is indicating to you that it was a dividing by, and so we put a negative in the exponent. Okay, so how do we convert kilometers per hour? Well, I'm going to write here kilometers divided by hours. What would that actually be? Well, a kilo is 1,000, isn't it? So it's 1,000 meters. And how many seconds are there in an hour? Well, there's 60 minutes in an hour. And each minute has 60 seconds in it. So when you're converting kilometers per hour to meters per second, you are simply working out what was the kilo. The kilo was 1,000. If you think about it, there are 1,000 grams in a kilogram. There are 1,000 meters in a kilometer. That prefix kilo is referring to 1,000. And an hour has 60 minutes, and each minute has 60 seconds. So if I'm converting to meters per second, I would have to multiply by 1,000 and divide by 60 multiplied by 60, because every minute has 60 seconds. So in our next line, I can leave that 1,000 at the top, but I'm wanting to work out the 60 times 60. So going across here, let's just make sure we have 60 times 60, and that's going to give me 3,600. So 3,600, and you may notice if I just was to cancel the noughts, it's going to get me to a value that is 1 over 3.6, or if you like, divide by 3.6. That looks like 36. It should be 3.6. Now, I want to encourage you, when you do this conversion, not to just say divide by 3.6 or times by 3.6. Get in your mind to work out what it is. And the reality is that in time, as you do these things quickly, you will certainly just type in your calculator, divide by 3.6 when you're going from kilometers per hour to meters per second. But very often students get confused and not sure, where was I supposed to divide by 3.6 or times by 3.6? Make sure that you can convert, I should say, from first principles, which means from what does the kilo mean? It means 1,000. What does the hour mean? It means 60 multiplied by 60. 60 minutes and 60 seconds. In doing this, you are showing you can prove the conversion, because very often questions, and I've seen this many, many times, the question will say to you, prove that 100 kilometers per hour is 27.78 meters per second. And they're giving you the answer, but they're wanting you to show that you understand the physics behind it, that there is 1,000 meters in every kilometer, and 60 multiplied by 60 to get that time conversion. So make sure you can do that. So now let's go and answer our question, which was this kilometers an hour to meters per second. We had to say, okay, it was 20 kilometers per hour, and I'm going to say times by 1,000 divided by 3,600. So going to our calculator, 20 multiplied by 1,000 divided by 3,600, and it's going to give me that answer. Now, I would never just write that down. I would always go and convert that, and so I would want it as a decimal, 5.55. So let's round off 5.56. So going back here, 5.56. My units, meters per second, and it is a speed. So do I have to write a direction? No, I don't. That is the speed. The next one, his velocity in meters per second. This might seem like a trick question, but it's not. It's asking you the velocity. Now, is the speed and velocity, is it going to be any different? No, he's going on a straight road, so his displacement and his distance traveled will be the same. He's going forward, so my answer here would be exactly the same, except meters per second, I need to write a direction. And if you haven't written the direction, you're not going to get your answer right, because a velocity is a vector. And so I have to give direction in my answer, because a velocity as a vector will have magnitude and direction, and you have to have that direction. Next one, how far he travels in 15 seconds. Well, this is interesting because now I've got a velocity, 5.56 meters per second, and I have a time of 15 seconds. Taking those two things into account, can I work out the last one, the displacement? Yes, I can, because that is how far he's traveling. And notice, what I would highly recommend whenever you come to motion problems, it was the same with waves. When you get given lots of information, write a list. Write down the information that you have, because that will help you answer the question. It will help you to see which equation do I need, what are they asking me. So I've written down my list, and I'm going to give myself more space at the bottom here. So let's give ourselves some space. And we had there, V was 5.56 meters per second, and time was 15 seconds. And I was asked how far, which is the displacement. So the equation I'm going to use is velocity or speed is equal to change in position over change in time. And I'm looking to find the displacement. So I'm going to need to take this to the other side. So V multiplied by delta T is going to give me change in position. And I'm just going to flip it around so that I can write at the bottom here. So velocity multiplied by change in time. Now we can substitute our values in. The velocity was 5.56 meters per second, and the time was 15 seconds. So going across to our calculator, and we have 5.56 multiplied by 15 is equal to some answer. We want it in as a decimal, so 83.4 meters. And so as he's going on his bicycle, he's covering 83.4 meters as the distance or the displacement, because it's in a straight line. The question said how far, and so I don't need to write a direction, although I could write forward. Here they didn't tell us if he was going north, south, east, west. They just said he was traveling on a straight road, so you can take it that he's going forward. The next question is asking me how far he travels in 20 minutes. And they give a sub-question there, give your answer in kilometers. So we've got a few things to consider. We've got 20 minutes. So I'm going to, once again, give myself lots of space. And let's write, let's write in purple. So we have, that is what I'm trying to find. The velocity or the speed has stayed the same. Meters per second. The time was now 20 minutes. Immediately, alarm bells are going in your mind. 20 minutes. Can I use minutes? No, we have to convert. So immediately you're thinking, they've given it to me in minutes, I'm going to need to convert, because we're always using SI units whenever we do equations or questions. So those are my values. Let's go. Velocity is equal to displacement, displacement over change in time. And I'm again working out the displacement, so I'm writing velocity times time. And I want to substitute in velocity 5.56 times by, and now I want to substitute in, well, it was 20 minutes, but each minute contains 60 seconds, and this value was how many meters he covered in 1 second. So I need to be working in seconds, and so once again Calculator, 5.56 times by 20 times by 60 is equal to 6,672. 6,672. What would the unit be here? It would be meters. Now, have I answered the question? And always go back and check. Have you answered the question? No, we haven't. They asked for it in kilometers. So if my unit is in kilometers, I need to jump from the decimal there 1 to 3 spaces, and so it's going to be 6.672 kilometers is how far he traveled. And that would make sense. He's cycling for 20 minutes. He's going to be, if he's going at 20 kilometers an hour, he's going at a pretty good speed, and he's going to go quite a far distance. Okay? So think about your answer logically. Does it make sense? Let's tackle the next question. Here we've got a car. It's traveling east. It accelerates from rest. So maybe you're thinking it stopped at a stop street, or it stopped at a traffic light. It accelerates from rest to 16 meters per second in 5 seconds. So foot on the accelerator, it's accelerating in 5 seconds. And so I'm going to be highlighting some keywords in 5 seconds. It then travels at a constant velocity. Again, that is helpful. For another time of 28 seconds. Before applying the brakes, that's helpful. What is that going to mean? The car must be slowing down to come to rest at another traffic light in a time of 9 seconds. Okay, I'm just going to put that little S in there. So, lots and lots and lots of information. Once again, I want to recommend to you that you write a list. Give yourself all those points as a list. Determine the car's acceleration in the first 5 seconds. Well, I want to break this motion down into a number of different stages. And so I'm giving myself some space here. Let's go from there. And often I actually sketch a scenario. So there's my little car, and for 5 seconds, it does something. For 28 seconds, it does something else. And then for 9 seconds, it does something else. So notice the car has got 3 stages of its motion. Let's write the information up. From rest to 16 meters per second. So it started here at 0 meters per second. By the time it got to the end of this 5 seconds, it was going at 16 meters per second. Throughout this whole distance, it's still going 16 meters per second. Throughout that whole time, I should say. And then from 9 seconds, it goes to rest. So 3 different stages of motion. What's happening here? It's acceleration. It's acceleration in this first stage. It's going to be a positive number. Okay, I'm just writing it as a plus. Through this intermediate stage, is it accelerating at all? No, it's not. Why not? Because it's going at constant velocity. Constant velocity. And then here we said it was decelerating. So my acceleration will be a negative. Here it was accelerating. And notice how a picture like this will help you get in your mind what's happening in all these different stages. So that first one, let's tackle the acceleration in the first 5 seconds we need to answer. All right, I'm dealing just with this first block. Okay? And we wanted to find its acceleration. So let's go. Acceleration is equal to question mark. I've got my list and I want to write an equation. Acceleration is equal to change in velocity over change in time. And I always start with that, with an original equation. Okay, so what values do I know? I know that its final velocity was 16. Its initial velocity was 0 because it started from rest. It started maybe pulling off from the traffic lights. And the time that it was going in was 5 seconds. So I've got 16 minus 0, which is going to be 16, divided by 5. 16 divided by 5 is equal to 3.2. Does that match my prediction? Yes, it does. 3.2 meters per second to the power of minus 2. Now I want you to notice here, does it meet my prediction? I said acceleration would be positive. Yes, it does. Why? Because it's accelerating. Is that my final answer? I want to check the question, because did they give us a direction? Because acceleration is a vector quantity, so it must have direction. Yes, the car was traveling east, and so my answer here must include direction. The next one was its displacement while it traveled at constant velocity. Let's write that in over here. We've got velocity is equal to change in position over change in time. I'm looking to find the displacement, so it's velocity multiplied by time, and the velocity throughout this whole period was 16, and we needed to multiply that by the time it took, so 16 times 28. 16 multiplied by 28, 448 meters. 448 meters. Again, you have to include direction, very important to include direction because they asked us for the displacement, which is a vector quantity. The last question on this is the acceleration during the last 9 seconds. So maybe the question could have even said the deceleration, because we're looking at this last point in time. And this last one, I want you to notice, again, I'm using the same equation. We're going to get a negative in our answer. Now, as I write this here, you need to identify why. Well, because I'm saying the final velocity minus the initial velocity. Recognize that the final velocity was 0. It got to rest. The car stopped at the traffic light. And the time was 9 seconds. So it's going to be negative 16 divided by 9. And my answer is coming out as a negative value. And that's important. It has to. If it doesn't, you've probably made a mistake. But I don't want to leave my answer there. I want to interpret what that negative means. So in this next point over here, you will notice I'm going to write 1.78 meters per second to the power of minus 2, meters per second squared. But I want to interpret what that negative means. It means the car is decelerating, and the acceleration, if you like, is west, in the opposite direction, because the car is slowing down. We're going to stop there with those questions, but what I want you to do is go and make sure you've done the challenge question, because we're going to do that after the break. Abram, over to you.
Thank you, Tracy. And after the break, we're also going to be announcing our Test Yourself Casio Calculator winner, so do stay tuned. Welcome back, Awesome Minds. This is now the moment that we've all been waiting for to hear our last week's Test Yourself Calculator winner. Drum roll, please, Tracy. And the winner for our show is Hamima Mullah. Hamima Mullah, congratulations. This Casio Calculator is coming your way. If you would like to be like her, make sure that you enter today. Back to you.
Awesome.
Tracy.
Mindset is, so today we're going to tackle the challenge question. And this was the experiment I asked you to do with a friend. So Abram and I are going to do the experiment together. As you can see, we've got our phones ready because this experiment is all about texting while driving. And lots of people will be like, oh, it was just a quick message. Not going to worry. And you see so many people, and there's laws out there that you're not allowed to speak on your cell phone while you drive, unless you've got a hands-free kit or something like that, because cell phones can be a huge distraction. And a lot of us will say, oh, but we can't live without our cell phones. Unfortunately, cell phones can be a huge hazard when people are driving. So the question is, we're going to do this experiment. How long does it take to text LOL on your phone? And then imagining if you were doing that while you're driving, because you're not. Because by the end of this, you're going to say, you'll never, ever, ever, ever. And if you see your parents or anyone else driving and texting while driving, you will warn them. Because we want to consider how far would a car travel while that person was texting. So I'm going to ask us to just quickly look through this question, join up with a friend and time how long it takes. The focus is we're timing how long it takes to type LOL single-handedly on a cell phone. We are going to record that data each time in a table, and we're going to make sure we have suitable headings in our table, and then we're going to calculate the average time it takes to type. So there's my table, and I've given lots of space. I'm going to give us a few readings. So reading, and this is going to be the time. How are we going to measure the time? What would be a valuable unit? I think in seconds, because Abram's pretty quick. I think you're going to be quite fast, aren't you?
I will.
He says yes, he knows his cell phone well. He's going to do it. So we're going to have reading 1, reading 2, reading 3, and then we will work on an average. Okay, so reading number 1. Abram, are you ready?
Okay, yes, I am ready.
You're ready. He's going to he doesn't even have to send the message. So if you can say, oh, you don't have airtime and you haven't entered the competition, well, make sure that you don't even have to send the message. Just time how long it takes. Okay, so tell me when you're ready.
Okay, ready?
On your marks, get set, go.
Stop.
Oh, that was really quick. 1.11. So our times here, 1.11 seconds. Notice when you fill this in the table, I'm not writing the seconds directly afterwards because the seconds is the unit in the heading. And we don't, as physicists, we're trying to save time all the time. We don't want that repetition of writing seconds every time. Okay. I'm resetting. Are you ready?
Yes.
On your marks, get set, go.
Stop.
Okay, that was even faster. 0.93. So 0.93. Let's reset. Last reading. Are you ready?
Yes.
On your marks, get set, go.
Stop.
And again, 0.93. So, very, very, very good. Well done, Abram. Thank you for your help. Mindset is, what we're doing here is we're getting 3 repeat readings and might be valuable to do even 5 or 10 readings. It's helpful because you always want to work with an average. You don't want to work with values that maybe the first value that you did, and look here, our first value was quite an outlier. Abram's very, very fast, and it might have been my slow reaction time in actually pressing start and stop on the stopwatch or the timing device. So notice here, it's incredibly important to work with averages and to do lots of repeat readings to make sure that our values are more reliable. So I'm going to grab the calculator and let's work out an average. Now, when you work out an average between your tests, you add them up and divide by how many tests you've written. In the same way, we're going to write all our values in plus 0.93 plus 0.93 is equal to almost 3 seconds, which it was, if you added those up, and I needed to divide by 3 readings, and it's going to give me 0.99 seconds. So my average here, 0.99 seconds. And that is the value that I'm going to work with as I go forward in this question. Okay, so we've timed, it takes 0.99 seconds, so pretty much almost 1 second to type LOL. Now, here's the crux. Calculate how far a car traveling at these given speeds would travel in the time that it takes. And what was the time that it took? We worked it out as 0.99 seconds. Now notice I'm not going to do this for each of my individual readings, but rather I'm going to work with the average, because that will be valuable. So what happens if the car was traveling at 60 kilometers an hour? What happens if the car was traveling at 100 kilometers an hour? What would happen if the car was traveling at 120 kilometers per hour? So once again, we're going to come and work with an equation. And the equation is velocity is equal to change in position over change in time. What am I being asked to find? How far it takes. So I want to work out the displacement, how far that car would go in that period of time. So so I'm changing the subject of the formula. I'm looking for delta x by itself, and so velocity is equal to delta x over delta t, and we're looking at that. Now, what is the velocity that I want to work with? Well, it was the 60 kilometers an hour, but can I just use the 60 kilometers an hour? No, surely I have to convert. I have to work with it in meters per second. So on the side, maybe over here, let's do it, and we're going to go kilometers per hour. Sorry. I need to convert to meters per second. And we did this earlier in the show. So I'm going to simply work in here 60 kilometers per hour divided by 3.6, or if you had worked it, it would be, maybe we can do it here, 60 kilometers per hour times by 1,000 divided by 3,600 is going to give me 60 times by 1,000 divided by 3,600 is equal to 16.67 meters per second, which means I can come along here, plug that value in, times by time, which was 0.99. Now, going back here, 16.67 times by 0.99 is actually quite far. 16.50 is actually quite far. And if you think about how far you would travel in that time while a person's texting, it would be very, very dangerous. A child could run in front of the road. Maybe the car in front of you stops. It could be incredibly dangerous, and that is why so many accidents are caused. So consider the science behind your everyday life, and don't ever text while you drive.
That's very important. Thank you so much, Tracy. That was so insightful and very educative, guys. So please share the knowledge also to your friends, your parents as well, so that we can create a safer environment, a driving environment for everyone. Well, Tracy, thank you so much, and see you next time.
See you next time. Thanks, everyone.
Right, thank you guys for tuning in. Really appreciate it. In case you missed any of our shows, schedule and notes, go to learn.mindset.co.za. We love you, and peace.